Okay, we are now recording. So 5035 MAA tutorial 2. And let's recall what we did last time is if you have a link with a certain mass that is rotating at a certain angular speed, omega, it will feel an inertial centrifugal force, F, which is equal to mass times acceleration. Now, the centrifugal force, it's an inertial force. Remember, it's the opposite of the centripetal force, which is mass times centripetal acceleration. And the centripetal acceleration is omega squared times r, where this r is also the link dimension. Okay, so this is what's happening if you have an out of balance mass that is rotating around a certain point. Now, what happens if you have a long rotor? If you have a long rotor with many masses, let's say you have support here, then you have rotors here, 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 and here. Okay. What happens here is that everything must be in equilibrium. Now, if I look at it from this plane, so if I look at it from the front, then I see this. Okay. If I look at it from the side, I see this. So my unbalanced masses are here or here or here, who knows, okay? Because they are rotating. So what happens now is that all of these forces, all of these things have their own force. So this is M1 R1 omega squared. This is M2 R2 omega squared. This is M3 R3 omega squared. And this is M4 R4 omega squared. So now we have to balance everything in all the planes. So what happens now is that we have basically we have the sum of forces that must be 0. Of course, all these forces must balance each other. But also, the moments of these forces around any point really must also be balanced. And how do you find the moment of a force about a point? Let's say we choose this point. It's completely arbitrary. Well, it's not completely arbitrary if you have to balance it. But let's take the moments about this point. Let's call this O. So the moment of M1 R1 omega squared, so the moment of the first force about this point is force times perpendicular distance. And this distance is L1. And then you have the moment of this force about the point. So the moment, this times L2, and so on and so forth. This is L3, this is L4. So you also have L3, you also have L4. So to balance these, again, it's MRL omega squared plus MR M2R2 omega squared L2, and so on and so forth. You take out all the omegas, because omega is common everywhere. And you are left with, so sum of moments, which is the sum of Mi, Ri, Li, omega squared. Omega squared can go away, so this is equal to 0. Since omega squared goes outside of the sum, because it's common, this 0, so you are left with the sum of Mi, Ri, Li equal to 0. And this is the MRL diagram. There you go. Of course, this is also withstanding the fact that you still have the sum of forces equal to 0. So this gets added to the MR diagram that we did last time. So both of these things must be satisfied at the same time. So this is the MR diagram, which encodes the sum of forces, and this is the MRL diagram, which encodes the sum of moments. equal to 0. All right? I mean, this should not be new. This is what you've done yesterday. Now let's solve the question. The question is this one, question 4. Let me make it larger and larger. There you go. So particulars of a system of revolving masses rigidly attached to a shaft are given in the table below. So remember, I gave you instruction on about creating tables last time. Now the table is already given, so we don't have to do much. So let me solve question 4. And question 4, I'll copy the table. Let me copy the table first, and then I'll show it to you. So plane, so this is the identification that I gave you last time. This here is called plane. So in plane A, the mass, which is in kilograms, always use units. The radius, which is in millimeters, and then we have MR, which is in kilogram millimeters. And then we have distance from A, so L. This is also millimeters. Ravi is asking, how do you know one force acting down as you have shown in the diagram? I don't. I just assumed it. I don't know it yet, because acting down, up, it doesn't mean down, up. You are in 2D, so you should look at where the mass is and the force is in direction of the mass. So you connect the unbalanced mass with the center, and that's the direction of the centrifugal force. Okay, so you have an X component and the Y component. You can't say it's up or down, because it can be on any direction in the plane. So you have to check. That's why we need the table. So ID MR, MRL, and also MRL, which is, of course, units of kilogram millimeter squared, as you can imagine. MRL, kilogram, millimeters, millimeters. So Ravi is still asking, so we can assume any direction. No, you can't assume it. It must be given in the table. See, this is 60 degrees. This is 135 degrees. This is 270 degrees. So it's not any direction. You have to actually, you have to know it. It must be given in the table. And also, finally, you have theta. Theta is in degrees in this case. Oh, guys, if you are here, did you swipe your card? You need to swipe your cards, because you have to take attendance. Especially if you are a tier 4 student. If you're not attending, you risk deportation. So it's a bit more dramatic, but yes, that's what you do. Okay, so you must scan your card. Okay, I'm still copying the table. So mass A is 6 kilograms, radius is 80 millimeters, distance from A. So since, of course, we are taking A as a reference plane, this is 0. Angular position is also 0 degrees. No, because I'm copying the table. Okay. I'm just copying the table as it is. So I have mass B, which is a 5 kilogram mass at 100 millimeters. And the distance from A is 130 millimeters and 60 degrees angle. And then we have mass C, which is 9 kilograms at 120 millimeters and 320 millimeters distance from A and 135 degrees again from A. And finally, D is 7.5 kilograms unbalanced on 60 millimeters radius and 490 millimeters from A and 270 degrees from A as well. Now find the magnitudes and the angular positions of 2 balanced masses. So we have to add 2 more. Okay. Remember, we have the MRL diagram and the MR diagram. So in order to balance a shaft completely, we need 2 masses, because we have 2 equations that we have to satisfy. For static balance, we had 1 equation And so you only needed one mass for static balancing. For dynamic balancing, you need both equations satisfied. So you need two masses, two balancing masses on two different balancing planes. So the two balancing masses, which I'll call L and M, because this is how we call them. So L and M. They must both be placed at 100 millimeters radius from the center of the shaft. Plane L is between A and B and 60 millimeters from A. So you can just say this is 60 millimeters from A. And plane M is between C and D, 140 millimeters from C. Now this we have to check. This is 140 millimeters from C. Okay, so this is what I gathered. So what we know is that the mass of L is unknown and the mass of M is unknown. I know that this is 60 millimeters from A. This is 60 millimeters from A. Remember, this distance here is given A as 0. That means 60 millimeters is from A. But this says it's 120, check. It's 140. It's 140 millimeters from C. Now, if C is 320, 140 from this is 460. Do you agree with me? So distance from A is 460. Because C is 320 from A, and then M is 140 further away from C. Agreed? Online students? Are you with me? Yes? What's the number for? The L. It's 60. It's this is ML 160. Oh, this one. 490. All right. So we don't know also, we don't know theta L, and we don't know theta M. Okay, so these are the unknowns. As you can see, we have two unknowns here and two unknowns here. So this can be solved because we have two equations. So one equation solves for two unknowns here, one equation solves for two unknowns here. Problem. The moment equation, if we write the moment equation like this, we have an issue. And the issue is that four unknowns will appear in the same equation. That's not good. But what we can do is change the reference plane. How do we change the reference plane? So I'm doing this. So this is L from A. I'll create L from one of the unknowns. So either L from L or L from M. Okay? So let's choose L as my reference system, as my reference plane. So this is also millimeters. And now I know that how much is the distance from A to L? It's 60, but if my L is 0, yeah, correct. If my L is 0, is my new 0, I have to subtract 60 from everything, basically. So this becomes minus 60. This becomes 70. Guys, I'm doing this by in my head, so make sure I'm doing this correctly. 320 minus 60 is 260. 490 minus 60 is 430. And 460 minus 60 is 400. There you go. So now we don't use these anymore. So these are now useless. Don't need this anymore. No need. Because now we are using these ones. Why are we using these ones? Because if I take the moment about one of these unknown planes, remember, if you take moments where the reaction forces are, the reaction forces won't appear in the equation because they will give no moment about that point. And so that's why it's very helpful to choose one of the balancing planes, either this or this, as our reference, because neither this nor this will appear in the MRL equation in this case. All right, good. So let me do this one. Let me do this. How do I do this? I don't know. How do I do this? Like this. There you go. So 80 times 6, it's 480 MR. And 5 times 10 is 500. And 120 times 9 is 1080. And 7.5 times 60 is 450. And this is 100 ml. And this is 100 mm. Oh. And now let's do the MRL. MRL is multiplication of this times this. Okay, this times this. And so we have 480 times minus 60. It's minus 28,800. Minus 28,800. And then this is 500 times 70. Oh, well, 35,000. Guys, please check my calculations as well. I know I'm using a calculator, but I'm also doing this very fast, so I might be wrong. So this is 1080 times 260. 1080 times 260 is 280,800. And then this is 450 times 430. 193,000, sorry. $500. This is 0. Oh, there you go. See, we did all this changing plane thing because now this is 0. Oh, nice. So we don't have to draw that vector, which is unknown. That vector is unknown. It should be 100 ml times something. But now that something is 0, we made it 0, so we don't need to draw this vector. But we need to draw this last vector, which is 40,000. Yes, 40,000 mm. Agreed? Agreed. Go away, go away. Okay. All right, now it's up to you. Okay, you have pen and paper, you have your square set, you have your protractors. I don't have any of these things, so I can sketch the solution, but you can actually solve it. Okay. So I will sketch the solution here. Let me take this down by a bit. So I will draw now. Is it possible to solve if you choose A as the reference plane? No, Mahmoud, this is not possible because see, what happens now is that I'm creating, say, a vector A at 0 degrees, as it say, then a vector at 60 degrees, then a vector at 135 degrees, then a vector at 270 degrees. So this is, sorry, this is red. Then a vector at 270 degrees, which is like this.
This one should be thrown.
Oh yeah, I know. I'll just do it. And then I have a, see, now, if you use A, so if you used A, this vector you would not have drawn at all, because A would be, MRL of A would be 0. But then you would be left with two unknown vectors, but two unknown vectors must close the polygon. But there are so many ways you can close the polygon, okay? So you have infinitely many solutions. If you don't take L or M as a reference plane, you end up with too many unknowns in the equation, and that means infinitely many solutions. Now let's do this properly. So let's start with A. MRL, so let's do, this is the MRL diagram. So MRL diagram. And I have to draw all these vectors. Now, the first vector is A, which is at 0 degrees, so it's horizontal, but minus 28,800. What does it mean for a magnitude to be negative? Okay, so it doesn't mean anything, because you can't have a negative magnitude, but that minus indicates that you have to add 180 degrees to the angle. That's the idea. If you get a negative sign in the magnitude, means add 180 degrees to the angle. So instead of going in this direction, A is going in this direction. So this is my first vector. And let's look here. The largest one is this one. And this one is 1/10 of this. So you choose a scale factor so that the largest vector can fit on your paper, of course, and all the other vectors ideally should be able to fit as well. So I know that this one should be 10 times as large as this. So let's make this quite short. And then we have 35,000, which is a bit longer than this at 60 degrees. And then I have the longest ones of all, which should be 10 times as much at 135 degrees. And then I have, again, very long one. So I'll take these, put it here. A very long one at 270 degrees. Shorter than this. Okay. And then you have 0, which you don't draw. And the last vector must balance everything. Okay. Does it make sense? Good. Now this is my sketch. This is my sketch of the MRL diagram. Let me put the labels, but before we do that, I want to check if L is the reference plane. Do we need to change the angles as well? No, because you are having the reference for the angle is still A. It doesn't matter. Okay. If you want, you can do this, but it doesn't add anything. It doesn't change. If you change the reference angle, what you're doing is just taking this diagram and rotating it around. Okay. So it doesn't change anything. All right. So I'll have a look at this solution because I want to make sure that this is the correct shape. So this is question 4, we said. Question 4. Would the vector 270 be pointing down? Ah, you're correct. Yeah, 270 degrees should be pointing down. Yes, you're right. Thank you. So let's this is 180 degrees. This angle here is not to 270. This is 270. You're correct. Thank you very much. So this should be pointing down. And so that means that this vector is this. So let me check if the solution is correct, or at least the sketch is correct. What is this? Question 6, no, question 4. Question 5, question 4. There you go. Yeah, almost correct. Okay, now this is actually done to scale. And this is how you should do it as well. Okay, A, B, C, D, and M. Yeah, now this looks correct now. Thank you, Mahmoud. And so we have, let's put the labels. So we have to label this. This is 180 degrees, and this is M1, R1, L1. This is 60 degrees. And this is M2, R2, L2. This is, guys, as you can see, it's always from the horizontal. So wherever your vector starts from, you draw an horizontal line, and that's the angle you have to take. This angle is 135 degrees. And this is M3, R3, L3. This angle, again, from where the vector starts, take the horizontal, and this is the angle, which is 270 degrees. And this is M4, R4, L4. And finally, this one is 40,000 mm. So you can measure it now. You can measure it. And you can also measure the angle. The angle is this one, theta m. Okay? So you now have your protractor. You use it to measure theta m. You have a ruler. Use it to measure the length of this vector. And then you know that, let's call this M, Rm, Lm. So this is the magnitude of this vector. And so you know that mm equals the magnitude of the vector divided by 40,000. Do you agree with me? Does this make sense? Yes? No? Guys? All good? Huh? As you can see, it's not very hard, and it's also fun. I mean, I find it fun. It's very fun at the exam as well.
So,
yes.
Around that top part there, is it the magnitude side of the two long lines?
Sorry, second.
The top part of that equation, the two long lines.
It's the length of the vector. Okay. So you have the length of the vector that you measure.
Yeah.
So you have to make sure that so you also have multiplied times the scale factor. Okay, so this thing must be measured in kilograms millimeter squared. If you measure this is 10 millimeters, then you have to convert it into kilogram millimeter squared because you have a scale factor. All right, guys, you have to practice this. Yes.
So are you telling me that MRL is always going to be a magnitude?
Yes. Yep. Okay. All right, so this was the MRL diagram. We now do the MR diagram. How do we do the MR diagram? Well, it's exactly the same thing. We take the other table, but instead of taking this column, we take this one. Okay. And the same angles. The angles are the same. We now have different magnitudes and a different scale factor as well. Right? So you have one scale factor here. Let's say, assume scale factor. Here you have that, let's say, 10 millimeters is 100 kilogram millimeter squared. So that means if you measure your vector and it's 3 centimeters, 3 centimeters correspond to 300 kilogram millimeter squared. Right? Again, this you need to find a scale factor so that your drawing fits onto the paper. Now let's do the MR diagram. And the MR diagram is, so let's look at the largest one. The largest one is 1080. So I'll have the scale factor here. Again, a different scale factor. You don't need to use the same scale factor also because they are different units. So I'd say that 1 centimeter on the paper is 10 kilogram millimeters worth of MR. So you know that this vector here must be 108 centimeters. It's probably too large. Okay, because 108 centimeters is a very long vector. So probably you want to make this 50. Okay, so for every 50 kilogram millimeters, you draw 1 centimeter worth of length. So let's start with A. A is 480. So let's make this 1 centimeter is, yeah. So you draw this. Nope. So this is M1 R1 and it's 480. I suggest you put all the values as well. I put labels here only. I suggest you put labels and values and the angle. So it's completely clear what you're doing. It's completely clear you're following the table and everything checks out. So the second one is B is a 500 long vector at 60 degrees. So it's about the same length, a bit longer at 60 degrees. Then we have the longest of them all, which is 1000. So let me put the labels as well. So this is M2 R2, and it's 500. And then we have the longest of them all, which is 135 degrees. So this is also 60 degrees. I have to take this down. This is 135 degrees. And this is the longest of them all, which is 1080 MCRC. What did I call it? 132. It should be A, B, C. Ah, my bad. And then we have the orange one, which is straight down 450, straight down 450, which is say half as much as this, and almost the same as MA array. DRD 480, no, 450, which is also 270 degrees. And now what's left? Well, if we look here, we have 100 mm, but mm we found earlier. Mm we found, it's here. Mm is this. How much is this? Well, according to the solution, is 5.25 kilograms. Okay, so this is 5.25 kilograms. So that means that this is 525. So this one is 525. I won't put it here, but I'll put it here. And it's at an angle of, according to the solution, the angle of this is 350 degrees. Okay? So do you agree with me? It looks like my drawing is almost on point. This is almost 350 degrees. And it's 525. So this is 350 degrees, about. So I have to draw at 350 degrees a vector that is 525. So it's a bit longer than this. So 525. This is M, R, M, and the angle is 350 degrees. Okay? And now the last vector is L. Now, I have skipped L and I've gone straight to M. Can I do that? Yes, why? It's just, so summation of vector is commutative, so it doesn't matter what's the order, at the end you still get the same thing. If you change the order of these, your diagram might look different, but in the end you'll get all the same vectors, just reshuffled around, okay? So it doesn't matter, we skipped L because we don't know it yet, but we know that L must close the polygon. So we know that L must close the polygon here. There you go. This is L. So this is ML, RL. And now you can measure this. This is the measurement, ML, RL. So the magnitude of this is in millimeters, which you can turn into kilogram millimeters given the scale factor. And so you can find that, sorry, it's not ml, RL, this is 100 ml. And so you know that ml is 100 ml divided by 100. This gives, according to the solution, this gives, yeah, it looks exactly like ours. Not exactly, but good enough. It's 8 kilograms and 233 degrees. It's about 8 kilograms. And this angle here, theta L, 233 degrees, as measured. Any questions? Now, see, the fact that I've drawn a sketch here, it's not exactly the same as the solution. It looks like that this M vector cuts into C, whereas in my drawing, not quite, okay? So make sure that everything is to scale. If you draw it to scale, it will look like this. So this is what, this was drawn to scale. This one, as you might imagine, I don't have a ruler. I'm doing this by eye, eyeballing this, and it's not quite the same. but almost. So let's make this a bit better so that it looks like the solution. So I'll take this one and say I'll put it here, no here. Take this one, put it here. And then I'll take these ones here. And I'll take this one. Just it's 525. Okay. Oh. There you go. All right. Now this looks a bit like the solution again. And also this one needs to be changed. Okay, any questions? Questions, guys, questions? No questions? All good?
Sir?
Right? Yes.
8 kg again?
Second?
8 kg.
8 kilogram.
Yeah, how?
How?
Yes.
You measure it. I mean, if you don't do it, you'll never know it. If you have to measure it with your ruler, okay? And then you get you change it with a scale factor in kilogram millimeters, and then you divide it by 100, and you get 8. Okay? All right. Now let's do 6, but 6, I want you to do, as I was saying. So do you want to have a break first or not? A little one. So I'll give you 5 minutes break. Is that okay? Yes. So I'll stop. I'll pause recording, and I'll give you 5 minutes break. Now we are solving question 6. A shaft carrying 4 pulleys in planes A, B, C, D. You can see here. Is to be balanced, I believe, by adding 2 masses, each of 5 kilograms, in planes L and M. Find the radii and the angular positions relative to A of these 2 masses for the system. Okay, there we go. So you have here, this is the polar diagram of the masses. So this is looking at the shaft from the side. So sorry, looking at the shaft from the front, and this is looking at the shaft from the side. So you have the position of the vector of the planes here, and then you have a squashed view of all the planes in 6a, figure 6a. So we can now create a table. Again, I'll copy the table from the previous exercise, just the first row. This is question 6. Yep. No, it's up to you. So this is what I'm saying. You can choose whatever mass as your reference mass. Okay, because it does, as I told you, if you change angle, you're just rotating your diagram. Your diagram doesn't change. You're just rotating it. So you choose which one of these masses you want to be 0. Let's choose A because it's the first. So if A is 0, B is 90 degrees, D is 135 degrees, and C is 90 plus 45 plus, so it's basically 360 minus 60 is 300. Okay? So let me see if I can do this on the 2 sides. I'll put this on one side, this on one side, and this looks horrible.
No.
So let's try like this, and then like this. Yeah, it's a bit better. All right. So let me put this down, and let me move my ugly face out of the way. There you go. So what I'm doing now is I'm saying mass A, so plane A, it's a mass of 15 kilograms at 10 millimeters. MR, I'll calculate it later. So we also know that we have two balancing planes. So let's choose one of these to be 0. Let's choose L because it's the first one. So the length, so the distance, the axial distance of plane A relative to plane L is, if this is 0, this is my 0. How much is LA? How much is LA? Come on, we have the, have we got the Californian student here? How much is LA? It's minus 200, okay? Yeah, minus 200. So you have, this is 0, so minus 120, minus 80. So A sits at minus 200. And theta, as we said, let's choose A as our reference mass for the angular position. So theta is 0 degrees. So let's start counting the angles from A. And now let's do B. B is a 12 kilogram mass at 9 millimeters. And it's at a plane which is minus 120 from L. And what's the distance from A? 90 degrees. There you go. So theta, let's put it here. So theta is with respect to A. It doesn't matter. You don't need to choose the same reference. You have one angle reference and one axial reference. Now, you tell me what's C. How many kilograms is C? 6. What's the radius of C? 8. And what's the axial distance of C? Axial. 100 millimeters from L. And what's the angle? Minus 60, or since we want the angles to be all positive, 300, because it's 360 minus 60. So 300 degrees. There you go. Minus 60 is also acceptable, but since we have always used positive angles, let's stick to it. And you tell me what's D as well. So what's D?
10 kilo.
Just a second, let me change color. This is D, 10 kilograms at distance, 12. Axial distance, 250. And angular distance, 135. There you go. You got the idea. I think you are 90% done with the exam, because that's it. It's not much. So we are left with L and M. How much is the mass of L? Well, that's one of the unknowns. No, is it unknown or not? It's 5 kilograms. But it's unknown what's the distance. So RL is unknown, RL. So what's the axial? What's the distance of L from L? That's of course 0. And what's the angular distance? Unknown. Theta L. Let's do M. Still a 5 kilogram mass at a distance unknown. What's the plane M? What's the distance? 350. And again, unknown. All right, so this is up to you. I'll do the calculations for MR and MRL, and then you draw the MRL diagram first. Can you draw the MR diagram first? Let's go back to the previous exercise. Can you draw the MR diagram first? No. Why? Because in the MR column, you have two unknowns, this and this. and this and this. You have 4 unknowns in the same MR diagram. Okay. If you look at here, you have you have this one and these ones. You have 4 unknowns in the same diagram. That's impossible. A vector diagram can solve for 2 unknowns. So you have to start with the MRL diagram. If you look at this only contains 2 unknowns. And then once you found MM, this only contains 2 unknowns. So you always start from the MRL diagram. And let's do the calculations. So this is 150, easy. This is 12 times 9, which is 18. 18, no, it's impossible. 12 times 9 is 108. Uh, 48, 120, and this is 5 RL. This is 5 RM. And the MRL, I'm doing this. For the MRL, I'm doing this times this. So this is 300, so it's 150 times 120, negatives, minus 18,000. This is 108 times 120, it is minus, not, oh, did I screw up? Yeah, yes, of course I screwed up. So 150 times 120, what? Are you sure? Oh, it's 200. That's so 150 times 200. Apologies, guys. It's minus 30,000. This is 108 times 120. It's minus 12,960. This is 4,800. And this is 120 times 250, 30,000 again. And this is 0. And this is 350 times 5. There you go. So we start with the MRL diagram because in this column we are using these 2 columns to draw the MRL diagram, and we have 2 unknowns. Why 2 unknowns? Because this one is 0, so you're not drawing anything. So you only have 2 unknowns, RM and theta m. And then once we found RM, we can find this value here. And so now the MR diagram only contains 2 unknowns. So let's start with the MRL diagram. And I suggest you use a scale factor of 1000. So I might say that scale factor, so 1 centimeter is 1000 kilogram millimeter squared. So that means that this vector here is 30 centimeters long. This vector is 12.9 centimeters long. This is 4.8 centimeters long. This is 30 centimeters long, and so on. Okay, second. I say, no, this is 30,000. Okay. Yes. Yeah. And I'll show you. So you have to draw a 30,000 vector in at 0 degrees, but it's negative, so it's 180 degrees. So I'm doing this now. It's 30 like this. So this is 30,000 at 180. Then you have 12,960. So let's say half as much. At 90 degrees. Then you have a 4,800 at 300 degrees. Is minus 60. 60 is this. Yeah. Second. Oh yeah, you're right. Sorry, apologies. The second line should go down because it's negative. Thank you very much. So it's not 90 degrees. It should be 270. So this goes down. Thank you. And then you have 135 degrees, which is longer. Okay. This is 4,800. Probably shorter even. And this is at 300 degrees. So this, you can say it's 300 degrees. This is 270 degrees. And finally, we draw this one, which closes the polygon. And this is 750 RM at an angle of this much t time. So let's make this larger. Okay, is this what we get from the solution? Let me check. Solutions. This is 5, this is 6, there you go. Yes, more or less. Oh, okay, so this looks like, it's like this. So this is more like this. And this is more like this. Is it down? I think it's not. It's 300 degrees. It's, yeah, it's going more down.
6 turns.
Yep.
You have only 5.
Second.
You only have 5 turns. You should have 6 turns. 1, 2, 3, 4. Well, I think the fourth.
Did I miss one?
6 vectors.
It's 1, 2, 3, 4. No, it should be 5 because this is 0.
Oh, okay.
This is the MRL diagram. So we're looking at this.
Oh, okay.
So this is 0. Okay. So the next one has got 6. So this goes here. Okay, you get the idea, okay? Let me put all the labels again. This is 30,000. This is 12,960. This is 4,800. This is 30,000. This is 0, and this is 1750. RM. So you know that RM in this case is whatever the value of 1750 RM divided by 1750, which is equal to, according to the solution, it's 5 degrees clockwork to A. That means it's 355. Yes. So theta M is 355 degrees. And RM is, it doesn't say, oh, 9.8 centimeters. So 98 millimeters. Okay, guys, apologies. For me, it's very hard to do this on the iPad. For you, it's much easier to do it on paper. It's probably take a bit longer because you have to be precise, but I think it's easier for you than it is for me. Now let's do the MR diagram. The MR diagram is just, let's use this column, this one, and the angles. So you now have 6 vectors. It's 150 at 0. I'm going to sketch this very, very quickly. So 150 at 0. Now we have 108 at 90. And then we have 48 at 300. And then we have 120 at 135. And then we have 98. So how much is RM? 5 RM? Yes. I found it here. 9.8 centimeters says. From, if you look at the solution, over 11. That's not too bad. Okay, because this I mean this is a graphical guys. A graphical method means you have large margins of error. Huh? Okay, so you should really do this on graph paper. If you do this on graph paper with proper square set and proper protractor, you get an accurate result. If you do this on that paper, okay, so probably the solution is wrong. I mean, it's not wrong. It's just that it wasn't done on graph paper. Okay. So can I inquire also online students? How much did you get for RM? Nice. Nice. How much did you get for RM? That table? 6. Okay. So how much did you get for RM? That table? Guys, hello. Oh, how much? Did you get? How much did you get for RM? Anything? No? How much did you get? No, not yet. How much did you get?
I don't do this.
Okay, you didn't do it. How much did you get? RM? 28. That's way off. No? Okay, you're doing it on, okay. Okay, so we got, so Umran got 9.9, Abdurrahman got 9.4. So you see, we are almost there. 9, 11 is fine. Again, at the exam, we are not expecting you get exactly right, but at the exam, we are looking for the shape that it should look right. The shape should look generally right. And your final answer should be within an ample margin of error. Okay? Yes.
Can we talk about that where m is equal to 9.8 centimeters?
Yes.
Because they use a different scale factor. One of the questions you
It
used
should-
5,000.
It doesn't matter. It's a scale factor. When you reconvert it back, you should get the same number. That's the idea. It doesn't matter. Scale factor is a scale factor. Okay? And also, Mario's got 10. So yeah, almost there. This. And finally, you get this. Okay, guys, this is how the MR diagram looks like. As you can see, the vectors can cross each other out. Okay, they can intersect, they can overlap. There is no rule that says vectors cannot overlap. Okay, this looks horrible, but it's completely fine. Okay. No, I was saying the vectors can overlap. It's fine. Vectors can overlap. That's completely fine. Okay, make sure you do this on paper. And please, 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 please practice. Okay? Because this is how you will be asked to do at the exam. On graph paper, that we cannot provide because you're doing this exam at home. So it's up to you to find some graph paper as well. How far off the analytical result is acceptable in the exam? Quite far off. Okay, it's more than 5%. We still accept it as long as there is no obvious mistake. We will still accept it. Don't worry. All right, guys, let's go to the next topic. Any questions? Any remaining questions on this? It's all clear? I mean, it's just a matter of laying it down on paper nicely. Good? Good. So let's solve. Lynn, what's the question for the... Say again? Oh, yes. 6 and 7. It's on the solution as well. So you said 6 and 7?
Yes, in the vibration.
Vibrations. Oh, come on. Why is it going on? What's going on?
It's quite simple, this section. Only for the vibration one.
What's going on? Oh, there you go. All right, vibrations. How was the vibration lecture? All right, yeah. So vibrations are my favorite topic, yeah, because my PhD is in structural dynamics. That has all to do, all of it has to do with vibrations. So let's delve into vibrations. So I'll give you a bit of a recap in vibrations. You might have noticed that if you have any system that has inertia and stiffness, so any system that exhibits inertia, mass, and stiffness it will feel a restoring force. So if this mass goes down, the spring will try to prop it back up. But since the mass has inertia, what happens is that this mass will overshoot. Okay, so if you pull it down, let it go, it will not return to the equilibrium position of the spring, because the mass having inertia will overshoot the equilibrium position, and then the spring will be feeling compression, and so it will be pushing it back down. But since mass has inertia, it will overshoot again, and it will keep overshooting forever because we don't have damping. Okay, there is no damping in this example, so it will overshoot forever. If you look at the equations of motion, free body diagram of this mass. So if the positive direction is this one, the free body diagram is this. So it only feels the restoring force of the spring, and that is Kx. So let's draw the equation of motion. Along the x-axis, the equation of motion is, how many forces are acting on this? Yeah, well, you'll say 2, but I'll say only 1 because this was already in equilibrium. The mg was already taken care of by the mass. Okay, let's make it easier. Let's say that this is an horizontal. So this is the motion, and this is the restoring force. And my system was this one. Okay? So the equation of motion along the x-axis is minus kx, because it's negative, it's going against my axis, it's a restoring force, equals mass times acceleration. What is acceleration? Second derivative of displacement. Displacement is exactly x. So this is the equation of motion. Very easy. We can rearrange this to look like this. Agreed? Okay. And now, what is this? This is the second derivative. So I can write this as mass times the second derivative of x of t in dt plus kx of t equals to 0. What is this? An algebraic equation? No. It is a differential equation. Yes. So how do you solve a differential equation? You need a couple of courses on. Okay. Yeah. There are many ways of solving differential equations. One of the ways is what you said. But one of the easiest ways is take a calculus course and learn how to solve differential equations. Or, since differential equations are all the same, these ones in particular have already been solved. So you don't need to solve it because we know the solution already. But we have to put this into a certain form to apply the solution. Mathematicians don't like the highest order derivative to have a coefficient. So let's get rid of this coefficient, which is in front of the second derivative. So I divide everything by m.
Oh, sorry, you're missing a square on the t at the bottom.
Oh, yes, you're right. Thank you. So this equation here, if we call this thing omega n squared for reasons that will be known now, the equation that I'm solving is x double dot plus omega n squared x equals to 0. And this equation here has a solution of x of t. So difference between algebraic equations and differential equations. The solution to algebraic equations are numbers. The solution to differential equations are functions. So the solution of this is a function of time. And that function of time is a sine omega nt plus phi. This is the general So every differential equation that looks like this or can be written like this, the solution is this one. And that's why we call this omega n squared, so that in our solution looks like omega n. Otherwise, we would have a square root in the, if we call this omega n, this would be square root of omega n, which looks horrible. Okay, that's why. Yes. It's this. Omega n squared is k over m. We called it like that. It's just a label that we attach. Otherwise, we have to say square root of k over m. Okay. You can also write this as where omega n is, of course, the square root of k over m. Okay, that's it. But what are a and phi? Well, a and phi are, well, those depend on the initial conditions. So this is how it looks like. This is a sine wave, but it's a sine wave that does not start from 0. It doesn't start from 0 because we have a phase angle. So if this phase angle is 0, then we have a sine wave, a pure sine wave that starts at 0 and oscillates indefinitely. If this is non-zero, of course, it doesn't start at 0. And if this is 90 degrees, this becomes a cosine wave because it starts here and then it goes down. Okay, so you know these things. There are other ways of drawing this solution. Another way is saying this is a sine omega n t plus b cosine omega n t. It's the same thing. You always have two unknowns. The two unknowns are a and phi in this formulation, or a and b in this other formulation. And these two are connected. Let's call this C because otherwise it's confusing. Let's call this capital X. There you go. So the two formulations are connected by the fact that A is just X sine of phi, and B is just X cosine of phi. Okay, so you can pass from one to the other quite easily. Okay, but let's not care about these. We will always be using this one because it's easier now, but in third year, you might want to start using this one because we have more manipulations to do. Now, this is without dumping. You didn't do dumping, did you?
No.
Not yet. Okay, so dumping is next week. Yes. Why do you add?
Yeah, why is that there?
Because you can write x of t like this or like this. You choose either this one or this one. It's omega n. Yes, omega n. Omega n is always this, square root of k over n. No, you don't need to worry about this one. This is just another way of writing it. Okay, now let's solve question 6. Question 6 is, of course, it's a single degree of freedom system that if you pull it down and release it, it will start vibrating. Do you agree? You have a spring, you have something with mass. It's not an equation as simple as this one, but we can turn it into an equation that looks like this one that we can solve. Okay? So let's do that. Let's do that. Question 6. And you need, of course, the free body diagram of this bar. So this is the, let me copy it first. Okay, a bar of mass 5 kilograms with a radius of gyration. What is the radius of gyration of something? Guys, first year, remember? Remember what we did, lecture 7 in 4025 MAA? Come on. Radius of gyration. What is the radius of gyration? What is the mass moment of inertia of something? It depends. Depends on the body. Every body has a different mass moment of inertia. Depends on the axis. But the radius of gyration is there to tell you the mass moment of inertia is always equal to the mass of the object times its radius of gyration squared. So this is just an easy way of giving you the mass moment of inertia without you having to calculate it. Yes. Yes, of course. You get all these equations in a sheet. And also you're doing this at home, so you can also open books. It's open books exam anyway. Okay? If you want, you can find everything. Huh? It's exactly like last year. Last year, okay, was open books, was all okay. I mean, you are here, so you all passed. It was okay. So what I'm saying is that O equals mr squared. So the mass moment of inertia of this thing is mr squared. So this is 0.7 meters. The mass is 5 kilograms. And the distance here is 0.5 meters from the start of the beam. And the stiffness of the spring is 200 newtons per meter. And that's it. What is the frequency of oscillation of the bar? So it's asking for the natural frequency, this omega n. What is omega n of this bar? So this is the information I have. And remember, we must make it look like this. So this is the final target. We want to target at the end something that looks like this. So how do you do this? Well, let's do the free body diagram of this thing. And first of all, is this a translational problem or a rotational problem? What do you think? Looks like a rotational problem. This bar is hinged here, so it will be oscillating in a rotational motion around O. All right? So, you know, if it's a rotational problem, it's all about sum of moments. So we will not even care about the sum of forces. We will do the sum of moments. But first, free body diagram. Now, let's draw this bar in a generic position, not the horizontal one, because this is the equilibrium position. At the equilibrium, the spring will not react. So let's make the spring react. So, and let's say that counterclockwise is positive, remember? So let's draw this bar in a counterclockwise and at a counterclockwise angle, say this one. And this is theta. Now, if the bar rotates at theta, here we have the reaction forces Ry and Rx from the pin. Remember, pin joints have two reaction forces, Rx, Ry, and this is still point O. And what's the direction of the force of the spring? Is it vertical or horizontal first? It's vertical. Yeah. And which direction? Is it up or down? Look at the deformed. So this is, if the beam moves up, the spring, what does it do? Pushes down. All right. So the direction of the force on the spring is this one. This is Fk. All right. All right. You also know that Fk is equal to Kx. All right. Sorry, let's say Ky, because this is the y direction, as I said, because it depends on this y. This is the y I must find, because as this y gets larger and larger, my spring reacts more and more. It's this y, not this y, not this y, not this y. It's the y where the spring is attached. Agreed? Good. What's that y? Well, let's take care about this later. Again, sum of forces equal to 0. So we know that Rx is 0, Ry is equal to Fk, but we don't care about this. We care about the sum of moments. We said it's a rotational problem. Therefore, we use that around the z-axis that is passing through O, the sum of moments around O equals, come on, Newton's second law for rotation, sum of moments equal, not 0. That's statics. This is dynamics. Sum of moments equal. Can you say it out loud, please? Okay, so you have the mass moment of inertia times the angular acceleration. Okay, so it's IO times alpha. Remember this? Now we have to repurpose this, but first let's find what is MO. How many moments? Look at these free body diagrams. Moments around O. Does this Rx give any moment around O? No, because it's passing through O. Does this Ry give any moment about O? It doesn't. Does Fk give any moment about O? Yes, it does. What's the moment of Fk about O? Force times distance. Vertical force times perpendicular distance. I'll call this A. Is it positive or negative? It's clockwise, so it's negative. So clockwise around O, that means negative. So it's this equation becomes minus Fk times A equals IO times alpha. Okay, this is still doesn't look even remotely like this yet. So we have to do some manipulations. So the equation is correct, but it doesn't look like this. So make it look like this. First of all, Fk, as I said, is Ky. So it's minus Kya. Let's say Kay. Let's just rearrange this. Equals M. I told you that IO is M R squared times alpha. Does this look like this? Not yet. This doesn't look like this yet. We can put this one on the other side. So yeah, that's fine. So we can say that M R squared alpha plus Kay equals 0. Still doesn't look like that. So what we can change? First of all, what is alpha? Angular acceleration. So alpha is just theta double dot. Agreed?
Yes.
Okay. So let's rearrange this. Does this look like this? Not yet, because if we have theta, if we have something double dot, we must have the same something without dots on the other side. Okay, so this we have something double dot, but this is not. But we have, yes?
How do you go from FK times A to A times A?
Because I told you that this is Fk is Ky. Okay, so Fk is K and Y, and the A is here. Okay, I'll just rearrange it. Okay, I was saying we have a kinematic relationship that links the rotation of the bar to the compression of the spring. Okay, this Y is the compression of the spring. So I can tell you that this Y, let's look at this triangle here. Let's look at the triangle. This is theta. How much is Y? This is A. Okay? Yes.
You know with the theta in your equation, you've got
Double derivative. Okay. So if this is A and this is theta, how much is Y? Yeah. How much is Y? A sine theta. So Y is A sine theta. But again, we can also say that this is for small oscillations. Do you agree that this bar, if I let it go, it will oscillate around the equilibrium position? So it will not swing up and down by a large angle. It will just vibrate just about the oscillating the equilibrium angle. Okay? So we can use the small angle approximation. So first of all, let's do this. So this thing becomes mr squared theta double dot plus ka squared, because remember this is a sine theta equal to 0. But now let's use small angle approximation. Means sine theta is almost equal to theta. And so now we have the equation that looks like mr squared theta double dot plus k a squared theta equals 0. And there you go. Now it looks exactly like this. Well, not yet, not precisely like this, but almost. What's missing here? What's missing here? We have to get rid of the coefficient of the theta double dot. So let's divide everything by mr squared. Okay, so this goes away. And now the final equation is theta double dot plus this beast and look at this. This is omega n squared, and this is omega n squared. All right? So I can say that omega n, so since now these look exactly the same, we just changed the symbol. Instead of x, we used theta, but it's the same thing. So we can say that omega n is the square root of k over m, well, k a squared over m r squared, where k is the stiffness of the spring, m is the mass of the bar, r is the radius of gyration of the bar, and a is the distance from the pivot point to the spring. Okay, so what happens if we take the spring and move it closer to the pivot point? Well, if you move it closer to the pivot point, it will oscillate with a higher frequency. No, with a lower frequency. Sorry, because this goes down. Okay? Yes.
The only thing I don't understand is A is the distance from the pivot point to the spring.
Yeah.
In the A cycle, that's the amplitude, A is the amplitude.
Yeah.
Are they both the same?
No, that's small a. This is small a. This a is just this. I can call this what the amplitude is capital A. Okay, or capital X. So what I'm saying is that if you want to draw the solution of this, the solution of this is theta of t is capital X sine of square root of k a squared over m r squared t plus phi. Okay, we don't know x and phi because I need to tell you how much I have pulled down, how many degrees I've pulled down the bar before releasing it. Okay, okay? Because if you look at this, if I pull it down by a small amount, it will oscillate by a small amount. If I pull it down by a large amount, it will oscillate by a large amount. Okay? That makes sense. That's what it is. For now, you're not finding the full solutions of things. You're just finding what's the frequency of oscillation, which is this omega n. Okay? Okay. Now, Let's do question 7. An object of mass 2 kg is supported by 2 springs, one of stiffness 20 kilonewton meters and the other 30 kilonewton meters. Kilonewtons per meter, sorry. What will be the frequencies of oscillation when the springs are connected in series or in parallel? Do you know the formulae? Series and parallel. Do you know where they come from? I mean, it's not hard. I'm sure you can do it yourselves. So let me put this here. Say this is solution. This is question 7. If you have springs in parallel,
you add them normally.
yeah,
Just normal slope.
you have springs in parallel like this, K1 and K2. What happens is that if I apply a force here, the sum of the forces of these two springs must balance the force that I applied. Agreed? If you do the free body diagram, you get that this is F, this is F1, and this is F2. So for equilibrium, F1 plus F2 equal F. So what I'm saying here is that for springs in parallel, you have that F equals, so the equivalent force is F1 plus F2, and you know that these are spring forces. So an equivalent spring of stiffness K equivalent times the displacement delta X, and they have the same displacement. So this is same displacement delta X. Okay, because if this goes up, both springs go up by the same delta X. And this is equal to K1 delta X plus K2 delta X. And so if I get rid of the delta X's, because I can do that, I get that the K equivalent equals K1 plus K2. There you go, solved. And these are for springs in parallel. For springs in series,
Inverse sound.
for spring in series is the force that's the same. It's not the displacement that's the same. So if you have a spring, an arrangement like this, and you apply a force, you have the same force throughout. Wherever you cut, it's always the same force. Agreed? They are all on the same line. There must be all the same internal force. So that means they have same force. So you have that F1 is the same as F2, which is the same of F equivalent. But the displacement is not the same. One spring will elongate more, one spring will elongate less. So what you have is that the equation becomes F equivalent is equal to F1 is equal to F2. That's what I said. And so F equivalent is K equivalent times the sum of the displacements, which is also equal to F1, which is K1 delta X1, which is also equal to X2, so to F2, which is K2 delta X2. And now we can just take, say, this part. Let's find delta X2 is K1 over K2 delta X1. And so I can plug this here. And I get K equivalent delta X1 plus K1 over K2 delta X1 equals K1 delta X1. So now I can get rid of the delta X1 because it's common everywhere. So I get rid of the delta X1 here, here, and here. And my new equation becomes that the K equivalent is equal to K1 over 1 plus K1 over K2. And if I multiply and divide this thing by K1, this and this go away, this and this go away, this goes here, there you go. Okay, I know it's a bit fast, but in the end, let's do this. So if you multiply and divide everything by K1, you get 1 over K1 plus 1 over K2. And this is exactly the solution for springs in parallel, in series, sorry. Okay, so in parallel, you use this. In series, use this. Okay, they come from different things. When you put the springs in parallel, they have the same displacement. When you put the springs in series, they experience the same force. Yes.
Zoom in on that last line.
This one. Okay. This should be on the slides as well, I'm sure. Is that wrong? What's wrong? Oh, so sorry, you were aren't this the same value? No, A and R are not the same value, because R is the radius of gyration. It's not here. If you look at the previous question, this is A. This is A. R is a different thing. R is the radius of gyration. It's a property of the beam. It's not a geometric thing. Yes. Yeah. The hypotenuse is A. The fact is, the movement is so tiny that the hypotenuse A is also the edge. Okay? Imagine this. This is why we can do this approximation, because the angle is tiny. So this one here would be A cosine of theta. Okay? But cosine of theta, if theta is tiny, is 1. Okay? That's it. So small angle approximation means that the sine of theta is theta and the cosine of theta is 1.
So when you did that, how did you get from that?
Because I divided everything by mr squared, and sine of theta is theta, as I said. Okay. All right, so let's do very quickly. Let's do question 7. I mean, I gave you the formula already. So what you have to do for question 7 is just find the equivalent. So we have the mass is 2 kilograms. So mass is 2 kilograms. K1 is 20,000 newtons per meter. K2 is 30,000 newtons per meter. And that's it. So says the first one is in series. So A series. So you have K equivalent is 1 over K1 plus 1 over K2. And that's equal to, guys, help me out. How much is this?
50 divided by 600.
50 divided by 600. Okay, that's
No, the inverse.
okay. So the inverse of this, is it 12?
Yeah.
12,000.
Yeah.
Okay. So 12,000. Guys, I am trusting one of you, okay? Okay. This is 12,000 newtons per meter. And so that means that the frequency omega n series is square root of K equivalent over m, which is square root of 12,000 over 2, is square root of 6,000. 6,000 square root, 77.46 radians per second. That's it. That's in series. Let's do B in parallel. So in parallel, we have that the K equivalent is K1 plus K2, which is 50,000 newtons per meter. And so that means that the natural frequency is the square root of K equivalent over mass is the square root of 50,000 over 2, which is 25,000 under square root 158.11 radians per second. Okay, this is very easy, extremely easy. Extremely easy as long as you know the formula, of course. Okay. All right, questions from the online students? Questions from the on-campus students? All okay? How was it?
All right.
Good? All right? Okay. Please practice, especially these kind of questions. Question 6. Please practice these ones. You have another one here. Question 8. Question 8 is quite interesting as well. Okay? So please try to solve question 8. I'll stop recording right now. Thank you very much, online students. I'll see you next week. Let me know if you have any questions. Bye.